Dear students, welcome to this class of Digital Logic and System Design. Today we are going to talk about the Boolean algebra. These are the basic postulates of Boolean algebra. They're also called as Huntington postulates. So Boolean algebra is an algebraic structure defined on a set of elements B together with two binary operations plus and dot. These are the or and operations, logical operations, provided the following Huntington postulates are satisfied. Now let us go through these postulates one by one. Number one, closure with respect to the operator plus. That means we have the elements that are 0 and 1. So whenever we carry out the or operation, the result is also contained within the set 0 1. That is what it says. We have seen in the previous lecture that the truth table for or is such that for all the possible input combinations, the output remains either 0 and 1. So this is what closure means. Similarly, closure with respect to the operator and, we have seen in that truth table itself that with respect to the AND operation, the results, the input combinations are either 0 and 1, and the output also is within 0 and 1. So this is what closure means. An identity element with respect to or designated by 0. So 0 happens to be the identity element of the or operation. Sorry. Yeah. And what do I mean by that? When I do x or 0, where x is a Boolean variable, it comes out to be equivalent to 0 plus x, that is 0 or x, and that is x only. So whenever I carry out the or operation with respect to the binary element 0, the output remains the same. That is what identity element means. If you remember, in the conventional algebra, the identity element for addition is 0. Anything plus 0 gives you the same thing, like 5 plus 0 is 5, 10 plus 0 is 10 only. Similarly, for the identity element for multiplication is 1. Anything multiplied with 1 gives you back the same thing. 5 into 1 is 5, and 5 maybe 12 into 1 is 12. So that similarly we have identity elements for the or operation, which is 0, and the identity element with respect to the and operation is 1, which means x dot 1 is equal to 1 dot x is equal to x only. So closure is the first property, identity element is the second property. Then commutativity. Commutativity is x plus y equals y plus x. Similarly, x dot y is y dot x. In the conventional algebra, we have commutativity with respect to addition and multiplication, but we do not have commutativity with respect to subtraction and division. A minus b is not equal to b minus a. Over here, we are saying in the Huntington postulate says that with respect to plus and dot, that is or and, both are commutative operations because of the fact that x plus y is y plus x and x dot y is equal to y dot x. Similarly, distributivity. Dot is distributive over plus and plus is distributive over dot. This one is something that we are familiar with. X dot y plus z will be x dot y plus x dot z. But this is something which is very unique with Boolean algebra. Plus is also distributive over dot. We are not familiar with this. X plus y dot z is equal to x plus y dot x plus z. So this is something new in Boolean algebra. Now coming to this, for every element x belonging to that set B, there exists an element x bar belonging to B called the complement of x, such that x plus x bar is equal to 1, and the second part, x dot x bar is equal to 0. So the concept of inverse element or the complement comes from this Huntington postulate. So any Boolean variable x, when ORed with its complement, the result is 1, and when any element x ANDed with its complement, the result is 0. Right? And the last of the Huntington postulates, there exists at least two elements xy belonging to B such that x is not equal to y. So that means this is defined on at least two elements, and in fact we know that it is defined on exactly two elements, not less, not more. It is defined on the elements 0 and 1. So these are the Huntington postulates: closure, identity element, commutativity, distributivity, if distributivity both ways, and for every element x belonging to be the inverse of it or the complement of it. And there are at least two elements on which this Boolean algebra is defined. Now if you notice here one thing before we move on to the next slide, that every Huntington postulate is given in two parts: A and B, A and B, A and B, A and B, right? A and B. So we will see in the next slide that this is called the duality. Let us move on to duality now. The Huntington postulates have been listed in pairs and designated by part A and B, just as I pointed out a little earlier. One part may be obtained from the other if the binary operators and the identity elements are interchanged, right? So whenever we are taking, you see, in order to get its dual, what do? We replaced plus by dot and 0 by 1. Similarly, let us move on somewhere here. So in order to get the dual expression, you have to change or to and to or. In fact, duality goes both ways, from A to B as well as from B to A. Both are the dual of each other, right? And whenever there's the involvement of 1 and zeros, you interchange them also. Over here you can see the dual x plus x bar is equal to 1. In order to get its dual, it will be x dot x bar, and this will be 0. And this is exactly what is happening. Or going backwards, x dot x bar is equal to 0. So we change it to or and change this to 1. So this is what the duality says. One part may be obtained from the other if the binary operators and the identity elements are interchanged. This important property of Boolean algebra is called the duality principle. It states that every algebraic expression deducible from the postulates of Boolean algebra remains valid if the operators and identity elements are interchanged. In a two-valued Boolean algebra that we have, the identity elements and the elements of the set B are the same, 1 and 0. The duality principle has many applications. If the dual of an algebraic expression is desired, we simply interchange or and operations and replace ones by zeros and zeros by ones. So this is a very useful property of Boolean algebra. You just have to, state one expression and the dual may be found out by simply interchanging or and operators and replacing ones by zeros and zeros by one, because these are the two identity elements. Now let us see the difference between Boolean algebra and ordinary algebra. Huntington postulates do not include the associative law. We have seen that. However, this law does hold for Boolean algebra and can be derived for both operators from the other postulates, which means, what is the associative property? X plus y plus z is equal to x plus y plus z. Similarly, x dot y dot z is equal to x dot y dot z. So this associative property does hold for Boolean algebra, just as it holds for the conventional algebra. It is just that it is not included in the Huntington postulates, but we'll include it later. The point of difference is the distributive law of plus over dot, that is x plus y dot z is equal to x plus y dot x plus z, is valid for Boolean algebra but not for ordinary algebra. We know that this doesn't hold for ordinary algebra. What holds for ordinary algebra is x dot, its dual, x dot y plus z. That holds for ordinary algebra. Whereas in Boolean algebra, both of them holds. Or is distributive over and, as well as and is distributive over or. Boolean algebra does not have additive or multiplicative inverses. Therefore, there are no subtraction or division operations, right? So we know additive inverse and multiplicative inverse we have seen in one of the postulates. So they only hold. We do not have subtraction or division operations. Postulate 5 defines an operator called complement, which is not available in ordinary algebra. Similarly, the concept of complement, digit wise, or bitwise complementation is not there in ordinary algebra, conventional algebra. Ordinary algebra deals with the real numbers which constitute an infinite set of elements. Boolean algebra deals, there are infinite real numbers. That is what ordinary algebra deals with. Boolean algebra deals with the as yet defined set of elements B, but in the two-valued Boolean algebra defined below and of interest in our subsequent units algebra, B is defined as a set with only two elements, 0 and 1. So it is a finite set that Boolean algebra deals with, and in fact this is a two-valued set on which it operates, two-valued, whereas the ordinary algebra deals with infinite real numbers. So these are the basic points of departure or difference of the Boolean algebra from the ordinary algebra. Now this was the postulate we have seen, identity element, postulate 5, just given in the form of a table. Postulate 5 you've seen, the inverse. Now let us move on to theorem. This is an interesting theorem. X plus x is equal to x. In the ordinary algebra, this is again the departure. You see, in the ordinary algebra, it would have been x plus x is equal to 2x, but there is no 2 in Boolean algebra, right? So we need to see that x plus x is equal to 2x is clearly invalid in Boolean algebra. So what will it be? That we have to see through the theorem. The dual, as I have stated earlier, you replace this by dot, and since there is no identity element, so no need to do that. So the dual of it will be x dot x is equal to x, again a departure from the ordinary algebra, because in ordinary algebra x dot x will be x square. Now let us try to prove this theorem first. X plus x is equal to x. We know that x plus x is equal to x plus x dot 1, the identity postulate, which is 2b, this one, x dot 1 is equal to x, so I can employ x plus x is equal to x plus x dot 1, which is again x plus x is retained, and 1 is x plus x bar, which is the inverse postulate, which is 5a. 5a, x plus x is equal to 1, so I just replaced it. Now what I'm doing is, this is basically the distributive property by postulate 4b, which is the distributive property. So I got it, x plus x bar, right? And x plus x bar, let me put it like this in order to make it more clear. X plus x bar will be x plus x dot x plus x bar. So you see, this is being obtained from the distributive property. Now x bar is 0. We have seen it from the postulate 5b. X bar is 0. So this will be x plus 0. Now x plus 0 is x. I have seen from postulate 2a. So ultimately I can prove that x plus x is equal to x. Now let us, since we have just started proving the theorem, so let us prove theorem 1b. Otherwise we would have simply got away by saying that since 1 is proved and its dual is this, so dual also is proved. We can say that. But let us see, in order to practice, x dot x is equal to x. So this is the postulate for theorem 1. So it will be similar lines, and you can see that all the arguments will also be the postulate. 2b replaced by 2a, 5a replaced by 5b, 4b replaced by 4a, 5b replaced by 5a, and 2a replaced by 2b. So since we are proving the dual, so the argument postulates are also the dual. Now let us see, x dot x is equal to xx plus 0. This is the same thing we have seen earlier. The absence of the dot means that there is a dot. So plus 0 by postulate 2a, because x plus 0 is equal to x, so xx plus 0 will also be xx. Now xx plus xx bar from the complement postulate, xx bar is 0, this one, 5b. So now from using the distributive property again, 4a, this is the distributive property, and x plus x bar is equal to 1 from postulate 5a. So this is x dot 1, and x dot 1 is x from postulate 2b. So I can prove that x dot x is equal to x. Note the theorem 1b is dual of the theorem 1a, and that each step of the proof in part b is the dual of part a. Any dual theorem can be similarly derived from the proof of its corresponding pair. So this also proves duality. You simply, whatever be the arguments, take the dual of that argument and you will be able to prove on similar lines in similar steps. Now other theorems 2a, x plus 1 is equal to 1. So x plus 1 is 1 dot x plus 1, right? The additive identity, sorry, the and identity. Now this one is x plus x bar, the arguments in terms the postulates are listed here. X plus x bar 1 is x plus x bar into x plus 1. Now you use the distributive property again. So x plus x bar dot 1, it will be the distributive property, because you see it will be x plus x bar dot x plus 1 if you go backwards. So now this is x plus x bar, because x bar dot 1 is x bar only, and x plus bar x bar is 1, the additive inverse or the OR inverse. So using these postulates I can say that x plus 1 is equal to 1. This is again a departure from the ordinary algebra. We have to remember this. In ordinary algebra, x plus 1 remains x plus 1. But over here, anything odd with 1 is 1. That is what it means. Anything odd with 1 will remain 1. Because we remember from the truth table of the OR operation that whenever a 1 exists, regardless of whether x is 0 or 1, the output remains 1. Similarly, theorem 2b, x dot 0 is equal to 0, that comes by duality. Or you can also prove it by having the similar steps with the dual postulates. Now this theorem 3 is very interesting. X dash dash is equal to x. The complementation of x, the double complementation of any variable gives you back the same variable. Now see, from postulate the proof is very interesting. From postulate 5 we have x plus x bar is equal to 1 and x dot x bar is equal to 0, which defines the complement of x. So this means the complement of x bar is x and is also x dash dash. This is by the definition of the complement. X plus x bar is equal to 1 and x dot x bar is equal to 0. So this shows, and since commutativity holds, that is why I can also write it x plus x bar is equal to x bar. Bar, when I say bar, I told you earlier, bar is something that you must adopt when you are writing by hand, and dash you can use when you are typing. In fact, while typing you can use both, but while writing it is advisable that you use bar for complementation. So I may say bar or dash, either of them, I mean the complement. So I was saying that commutativity, x plus x bar can be written as x bar plus x is equal to 1. So which means just as x dash is the complement of x, similarly the complement of x dash is x also, both from these 2 points, right? Just as I can write x dot x dash is equal to 0, similarly I can write x dot x dash is equal to x dash dot x is equal to 0 by commutative property. So this means that not only x dash is the complement of x, but also x is the complement of x dash. So by definition, the complement of x dash is x by these two definitions, and by notation, the complement of x dash will be x dash dash, right? And since the complement is unique, we can conclude that x dash dash is equal to x. So interesting proof, interesting proof. On one side, I'm using the definition to say that the complement of x dash is x. And from the notation side, I know that the complement of x dash is x dash dash. And since they are unique, so I can conclude that x dash dash is equal to x, right? Now theorem 6a, x plus xy is equal to x. Again, interesting part, because you do not see this in ordinary algebra. Let us see x plus xy is equal to x dot 1 plus xy. You can AND it with 1, gives you the same thing, the and identity element. Now using distributive property, you can say that x 1 plus y. Okay, you can take x common, so 1 plus y by distributive property. Or this may be x y plus 1, right? Now anything odd with 1 is 1 itself. We have shown it here, the dual part of it. So sorry, yeah, the dual part of 2a. So that is what I've seen. No, but this one itself, 2a itself, not 2b, 2a itself. So y plus 1 will be 1. So x dot 1, and again the identity element that will give me x back. So x plus xy is equal to x, right? The dual part of it, x into x plus y. How do you found the dual part? You replace this or with and, this is here, and this and with or. So this will x plus xy, the dual would be x dot x plus y, right? And on this side it will remain x, because there is no and or operation, there is no 0 1, so this remains. So by duality I can say that x into x plus y is equal to x by duality. So these were some of the theorems that we have proved. The algebraic proofs of the associative law and De Morgan's theorem are long and will not be shown here. You see, let us just look here. Distributive, we have, this was the postulate. Postulate do not need any proof. Theorems do, right? We have proved theorem 1, we have proved theorem 2, we have proved theorem 3. Double complementation gives you the same variable back, and this is called the involution theorem. Commutativity is a postulate. Associativity is a theorem. Similarly, distributivity is a postulate. So we need not prove it. But De Morgan is a theorem that we need to prove. Absorption we have just now seen, x plus xy is equal to x. So these two theorems, associativity and De Morgan's, need to be proved. Let us have a look at these steps. The statement of it. X plus y plus z is equal to x plus y plus z. I have shown it in the previous slide also. Similarly, xyz is equal to xy dot z, right? This is one thing. De Morgan's theorem is very useful and is, is one of the very important theorems in Boolean algebra. It says that it talks about the complementation of a Boolean expression, x plus y whole bar whole dash. Complementation of the whole will be x dash y dash. So you will change the and to or to and also complement the individual elements that were there. Similarly, xy whole dash will be x dash plus y dash. Hmm? This, there was this and in between, so that has been changed to or, and they have been, individually complemented as well. So De Morgan's theorem is very important. So associativity and De Morgan's are two theorems that are left to be proved. So they are saying that algebraic proofs of the associative law and De Morgan's theorem are long and will not be shown here. This is beyond the purview of this course. However, their validity is easily shown with truth tables. For example, the truth table for the first De Morgan's theorem, which is x plus y whole bar is equal to x dash y dash, is shown below. You took xy, all the possible input combinations. There are just two combinations, four combinations possible: 0 0 0 1 1 0 1 1. Out of it, x plus y, this is the truth table of or, and x plus y bar will just be the complement of it, which will be 1 0 0 0, right? So we've got the left hand side. Now let us look at the right hand side. X dash complemented 1 1 0 0, complemented, it will be 1 0 1 0, and you take the and of it. 1 dot 1 is 1, and anything ANDed with 0 will be 0. So there is at least 1 0 here, so it's 1 0. Now you see this row and this column and this column are the same. So that means they are the same, because we're talking about the truth table, which exhausts all the possible combinations. So this shows the validity of the De Morgan's theorem. Once its validity is shown, its dual also holds, right? So associativity, De Morgan's, they can be shown using the help of truth tables, because their proofs are too long to be discussed here. Rest of the proofs of the theorem, basic theorems, we have seen already. One important thing is the operator precedence. Remember, in the ordinary algebra we have bracket of, you know, division, multiplication, right? Addition, subtraction, board mass we used to remember, right? So similarly we have some operator precedence for Boolean algebra also. It is parenthesis first, followed by not, then and then or. So remember this precedence. These are, you know, these are just three operations plus the parenthesis. In the case of ordinary algebra we also had multiplication and, you know, division, subtraction and division. So we had to incorporate them also over here. We just have these three basic operations. So the operator precedence will be like this: whenever any Boolean expression is given, we will first evaluate the parenthesis, then we will evaluate not, then we will evaluate and then we will evaluate or. So this will be the operator precedence for Boolean algebra. So a lot of things to remember from today's lecture. So please, you know, follow this lecture very closely and make your own notes. Now, these are some of the examples that I've worked through. X plus x dash y can be written as x plus x. This can be written as x plus x dash. This can be written using distributive property, right? So this step follows from this using the distributive property. Okay. Now x plus x dash is 1. So 1 dot x plus y, so x plus y. So I can say that x plus x dash y is x plus y. This is not a standard theorem, but a useful result nevertheless. So I can say that x plus x dash y is x plus y. By distributive property, I get this. X plus x bar is 1, I know that. So 1 dot x plus y, you know, the identity element. So this remains x plus y. Similarly, x dot x dash plus y. Again, the distributive property, this will become x dash plus xy. So x dash is 0. So this 0 plus xy will be xy. So this in fact is the dual of this, but still I can prove it. Dual because I have replaced this plus by and this dot by plus. So I get this, and the result part I have replaced this or by and. So I got this in fact 2 is the dual of the first one. Now involving three Boolean variables x dash y dash z plus x dash y z plus xy bar, I can work through it. I can say that x dash z can be taken as common. So what remains is y dash and y, right? So y dash plus y. So these two can be combined together using distributive property and xy bar is there. So now y dash plus y is 1, right? So when this is 1, so this becomes 1 x dash dot x dash z dot 1 and x dash dot z, anything ended with 1 is this thing itself. So this will give me x dash z plus xy dash that remains at its place. Xy plus x dash z plus yz is equal to xy plus x dash z, these are intact. Yz I can write as yz into x plus x bar because x plus x bar is 1. So I can write yz dot 1 which is x plus x bar. Now xy plus x dash z, this part remains the same. Now using distributive property, this becomes xyz plus x dash yz. Now I can take xy common. When I take xy common, I get 1 from here and z from here. So xy into 1 plus z. Whenever I say take common, that means I'm using the distributive property, right? So and plus I can take x dash z common. When I take x dash z common, what remains is 1 from here and y from here. And I know that 1 plus anything is 1 only, and 1 plus anything over here will also be 1. And anything ended with 1 remains, give me the same thing back. So this will be xy and this will be x dash z. So this entire expression can be simplified or minimized like this. And you take the dual of it, x plus y, replaces and by or, this or by and, this and by or, and this or by and this and by or. So I get the left hand side of the given expression. Now let me go on to the right hand side. So this will become x plus y and this becomes and, so x dash plus z by duality from function 4. So these are some of the examples that I have taken up. So we will stop here and try to go through our lecture today very, very carefully, because this is a very important lecture. A lot of things have been covered and we need to practice these things. We need to memorize these things. So please do that before we meet for the next lecture. Thank you very much.